Hey guys, welcome back from spring break. It's Professor Winans, and I'm going to go over some of the things that you need to know for this week. So this week we were going to be talking about essentially finishing up Unit 6. So if you remember, before we left for the break, we had gotten up through sliding filament theory. I wanted to review that for you just to make sure that we all refresh our memories. It's been a little while. And then I want to build on that. So you're going to want to read the slides again before you watch the videos so that all of this makes sense to you. And then just use your slides to kind of follow along. I'm not going to go over everything in the slides so you don't have hours of video to watch, but I'm going to go over the concepts that I think need explaining. So this will be the first in the series of videos, and this is just our review of sliding filament theory. So here we have a sarcomere, and remember that's the functional unit of skeletal muscle, not only skeletal muscle, but also cardiac muscle. So we have our structural proteins, or our stabilization proteins, the Z lines on either side, and then we have an M line in the middle. And these are there to just hold everything in place to mark the ends of the sarcomere in the case of the Z line, and to hold the middle of the sarcomere in the case of the M line. Now the orangish color, the thicker filaments, that would be the myosin, and the green here, the thin filaments, that would be the actin. And the idea is that when we have a contraction, we have in the muscle cell just hundreds and hundreds of these all lined up end to end and all around each other and all in the 3D sort of way around each other. And when you have the contraction, it's going to shorten. So each sarcomere will be pulling the Z lines in towards the M line, and then when you relax, the Z lines come back out again. So that's why they call it sliding filament theory. Now down here we have the close-up of our actin and myosin, so we can understand or review how we actually shorten the sarcomere. So if we look at the myosin, we've got our myosin heads attached to the myosin tail, and the tail would be all interwound with other myosin tails. So you have lots and lots of tails all wound up together, making the straight structure here, and then heads sticking out like a little bristle brush all over the place. The actin now, the actin is something called F-actin, and each little ball of F-actin, if you think of it like a beaded necklace, each little bead would be called G-actin. And on each G-actin, we have a binding site for the myosin heads. Should have wrote that before, forgot. Okay, so normally when the muscle is at rest, you have the binding site for the myosin heads on the G-actin covered by two proteins, trypomyosin and troponin, and together they make the trypomyosin-troponin complex. But then when you have an action potential, we're going to move that complex aside so the myosin head can bind. And this would be where you want to go back over how you have the action potential that's carried by the T-tubules really quickly all throughout the cell, reaches the terminal cisternae where you have calcium stored, calcium is released from the terminal cisternae, all that stuff we went over right before we left for break, or the week before we left for break, so it's been even longer than that. So go back over that. So we have our calcium bind to troponin. It moves trypomyosin and troponin away from the binding site on the myosin, on the actin, so that the myosin heads can bind. And we call that cross bridge formation because we're creating a bridge, essentially, between the myosin and the actin. Now, so once we have our cross bridges formed, so imagine all these little myosin heads sticking up all over the place. I'll just do them right there. And they would be bound to the actin in this zone of overlap here where we have actin and myosin able to interact. So those myosin heads will bind to each little G-actin molecule in the binding site, making that cross bridge. And then when you have the cross bridges formed, the myosin heads pivot in towards the M line. So they just kind of ratchet in one step. Then, if you still have a stimulus going, so you're continuing the stimulus, you have the action potential still creating the release of calcium from the terminal cisternae, So we still have calcium bound to troponin. Those myosin heads will unbind. They'll pop back up to the original position. They'll bind onto the next piece of G-actin, pivot inwards. That pivot inwards is called a power stroke. And each time you have a power stroke, so one power stroke is equal to a twitch. Okay? So every time you pivot in, it's a twitch. So it grabs, pivots, that's a twitch. Let's go, grabs, pivots, another twitch. And in order to have an actual full motion, you have to have lots and lots of these twitches added up together, happening repeatedly over and over again. So our twitches are added up to create a contraction. And that process of adding twitch upon twitch is called wave summation. Okay. Now wave summation can result in something called complete tetanus. Switch colors just to keep it flame. So we can have complete tetanus. Sorry, complete tetanus, and that is maximal tension. And this is caused by maximal stimulus. So if you keep stimulating the muscle quickly, you can create the most tension possible. Now, if we have a situation where we have something called submaximum stimulus, we would have something called incomplete tetanus be the result. And this is anything less than maximal tension. So anything short of stimulating it maximally will give you an incomplete tetanus. So not as contracted as it possibly can be. Complete tetanus is where it is contracted as much as it possibly can be. So if we go back to our sarcomere, we think of shortening the Z line all the way until it butts up into the M line. That's as short as it could possibly go. That would be complete tetanus. But maybe we just shorten it to here or here or here. Doesn't matter. Anywhere short of that complete shortening, that full tetanus would be incomplete tetanus. It would be a submaximal stimulation. Now another word for maximal, or thinking of the most stimulus you could have, we could also call that liminal stimulus. So we could just use that word also. So that's a vocabulary word. If you look in your lab book, you'll see that popping up. So liminal stimulus, and therefore if we have a situation where we're coming up with incomplete tetanus with something less than maximal tension, so submaximal tension, it would be called subliminal stimulus. Liminal stimulus. Okay, so how do we end up with maximal stimulus or submaximal stimulus? And the answer to that is how quickly you stimulate the muscle. So if you stimulate it again really, really quickly, you're going to end up with a situation where you have maximal tension. If you stimulate it again a bit slower, and let's use this side here, let's redraw our sarcomere right on top of the old sarcomere that I had on here. We'll think of how we can end up with something less than complete tetanus, something less than submaximal tension. So if we think of each twitch as having a phase, we have a phase of the twitch where we've got just the action potential arriving and calcium being released. So nothing is really happening in the sarcomere yet. We're just letting calcium out of storage. That's called the latent period of the twitch. And I'm going on slide 11 now. We're going a little bit forward. After the latent period of the twitch, we end up in the contraction period, and this is where the calcium is out in the cytoplasm. It's binding to troponin. Troponin and tropomyosin are moving away from the active site or the binding site on the actin so that the cross bridges can form with the myosin heads binding, and then they pivot with that power stroke and you develop tension. So you shorten the sarcomere. So you're taking the Z lines and pulling them in. So that's where we grab, pivot, release, grab, pivot, release. That's the contraction period. And then with the relaxation period, that's where we release the cross bridge and we start to have the actin slide back out again. So the Z lines are opening out. So we twitch in during the contraction period, and then during the relaxation period, we release and slide back out again. Now, if we do this really, really fast, we don't get an opportunity for it to really relax very much. So we twitch, 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 twitch in towards the center. That would be maximal stimulus leading to complete tetanus. If we allow it to relax a little bit before we stimulate it again, we're not going to be able to get it all the way as tight as it could be. So let's just have a little twitch, and then we let it relax a little bit, and then we twitch again, and we relax a little bit, and we twitch again. So we're adding the twitches still, but it's just not as tight as it could be. It's not as much tension being developed as it could be. So that is how we would end up with something like incomplete tetanus. Okay, so that is it for sliding filament theory, and our next video will be about smooth muscle, and then we'll have a video about cardiac muscle, and then also reflexes. Okay.